Hello and good afternoon, friends. Welcome to the CEC-UGC live lecture. Dear friends, as you know that we are carrying a series on chemical thermodynamics, and so far we have conducted numerous lectures, and with the help of these lectures we hope that we have helped you out in studying your course material. Dear friends, as you know that we have already conducted numerous lectures, today we are going to start with another topic under the series, that is thermochemistry. What is thermochemistry? Today we are going to understand about this very concept of thermochemistry, and we are going to conduct more lectures on thermochemistry. But as per as today is concerned, we are going to start from the very beginning, and for this we have again with us in our studios Dr. Amit. Dr. Amit is assistant professor, senior assistant professor in Department of Chemistry, Dal Singh College, University of Delhi. So dear friends, let's take advantages from his experiences and let's try to understand more about thermochemistry. Hello sir, welcome to the EduSet lecture.
Thank you very much. Dear friends, we have been having a number of lectures in the topic matter of chemical thermodynamics, where we had started with the basics of chemical thermodynamics, after which we had also studied the first law of thermodynamics, and we did see that with the discussion of expansion work, and we had formulated the concept of important state variables of the system, that is its internal energy and the enthalpy. And we have also seen that how the energy of a system varies under different conditions. And we have formulated, if a system exchange heat with the surroundings under condition of constant volume and constant pressure conditions, it lead to a change basically in the internal energy, and the enthalpy changes becomes important in those heat exchanges when a system bring about heat exchange with the surrounding. So now today we have to now focus our attention straight away onto the chemical systems. And the chemical systems which we deal with, they are dealt with in a separate topic called thermochemistry. So let us see what thermochemistry is all about. Thermochemistry primarily deals with the transfer of heat between a chemical system and its surroundings when a phase transformation or a chemical reaction takes place within the system. What I mean to say by this is that, suppose for example, if we have a system, and in the system we carry out certain chemical reaction, or a phase transformation means a chemical substance undergo a change in phase from solid phase to liquid phase, or vice versa, or it can undergo, a liquid phase can undergo conversion to vapor phase, or other way around it could also be, or a solid could also directly convert to a gaseous phase and then and the gases can also be condensed to straight away to solid systems. So all these are examples of phase transformations. So whenever in a system a phase transformation occurs or a chemical reaction occurs, then of course a change in state of system is being brought about by virtue of this chemical reaction or the phase transformation, or phase transformation is a physical process. So therefore, when a change in state occurs, of course the change in state would be there by virtue of change in state variables, for example the temperature, the pressure and the volume. And therefore it is important to understand what were the conditions for a reaction or for a phase transformation which was going on in the system. If the conditions are such that volume of the system is being kept constant, that is we are dealing with only closed systems, then in that situation, under constant volume conditions, we have already seen earlier that when a system exchange heat with the surrounding, then that exchange of heat between the system and surrounding can be related to the change in the internal energy of the system. On the other hand, if the pressure of the system is kept constant, then in that situation the heat exchange by the system with the surrounding can be related to the enthalpy change of the system. So therefore, now if we just focus our attention to our chemistry laboratory, in all the physical processes which we carry out, for example melting, the boiling of a liquid, the melting point we try to observe, all these are examples of phase transformations, and these are done in open systems. That is, if for the purpose of determination of melting point, what we do is we take a capillary, close it at one end and fill it with the solid substance whose melting point we need to determine. We bring it to a medium where we supply heat to the system in that manner, and then it undergoes, it takes up the heat, and ultimately a temperature is reached where the solid substance undergoes melting. So that is its melting point. So basically this phase transformation is occurring, what I mean to say is occurring under constant pressure condition. That is, we are dealing with only open vessels. Moreover, when we carry out certain chemical reactions, they are, most of them we carry out in laboratory under open conditions. So that is again, the atmospheric pressure becomes the prevalent pressure of the system. So therefore pressure is again constant there. So it is therefore very clear that for most of the chemical reactions which we carry out in our laboratory under constant pressure conditions, the heat exchange with the system can be related to the enthalpy change of the system. And in system, what is going on, a chemical reaction or a phase transformation, so that enthalpy change of the system ultimately can be related to the enthalpy of the reaction or the enthalpy of the phase transformation. So if we need to understand the or quantify the enthalpy of a reaction, then we need to give symbolic representations to the molar enthalpies of substances. Let us have a look at how we give symbolic representation to molar enthalpies of a substance. Suppose we want to represent molar enthalpy of a substance. Let us say the substance is B. Symbol B is given for the name of the substance. So molar enthalpy of a substance means the enthalpy for 1 mole of a substance B and is represented by symbol H subscript M. Hm means molar, H is the symbol for enthalpy, therefore molar enthalpy. Molar enthalpy in parenthesis, that is followed by parenthesis within which the name of substance is written, that is B, HMB. So therefore HMB is the symbolic representation for molar enthalpy of substance B. Not only this, that we just described the name of the substance, but it is also important to give other physical characteristic of the substance. That is, we need to specify what is the physical state of the substance which is present in the system. Moreover, we need to specify the temperature of the system as well as the pressure of the system. Then it becomes the complete description of molar enthalpy in the symbolic representation. For example, if we talk about molar enthalpy as a variable of water, that is at 393 Kelvin at 1 atmosphere pressure, then what we need to do is we need to write Hm, that is the symbolic representation for molar enthalpy. And within parenthesis we have to write the name of substance. The name of substance is water. So Hm, H2O water, that needs to be separated by virtue of comma with the physical state of the substance, that is the solid, the liquid or the gas. So we all know that at 398 Kelvin, that is above 373 Kelvin, the water exists in the form of gaseous phase. So therefore at 398 Kelvin it would exist in the gaseous phase. So we just write the physical state of substance, that is represented by symbol small g, which stand for gaseous state, and then needs to be separated with a comma, and then we need to describe the temperature, that is 398 Kelvin, followed by the pressure, that is 1 atmosphere pressure. So this is all about the symbolic representation of how we represent the molar enthalpy of a substance in the representation of symbolic, in the symbolic representation form. Now, having said this, so therefore it is very important to understand, since enthalpy is a function of temperature and pressure, therefore molar enthalpy of a substance is also a function of temperature and pressure, and therefore this pressure dependence. So if we want to vary the molar enthalpy of a substance, there are two options. One is that you can increase the temperature of the substance, then its molar enthalpy will vary, and also the molar enthalpy will also vary if you vary the pressure of the substance, which that is implied on the substance. This pressure dependence is removed by defining the standard state of a standard state of a substance. If suppose a substance is present under constant pressure condition. So, in that situation the second variable, the pressure, which on the basis of which the molar enthalpy varies, since this is kept constant, then in that situation molar enthalpy will only be a function of temperature. And let us see how the molar enthalpy of a substance varies. In order to understand how the molar enthalpy of a substance varies, let us first of all consider the heating curve. That is, if suppose in a test tube, for example, we have a solid substance, pure crystalline, any pure crystalline solid substance, for example a benzoic acid, then we suppose we try to heat it in a sand bath, then what will happen? Its temperature will rise. So, you can see we can record the temperature of the system with time, and with time what we are doing? With time we are heating the system. So, as we heat the system, the temperature of the system increases. Now, you can see this is the temperature, this is the line of temperature, the temperature of the system becomes this, and when you at another time the temperature of system becomes this, and then it continuously rises and ultimately reaches to point A. At point A, if point A represents the melting point of the substance, so when a substance undergoes melting, a pure perfectly crystalline substance has a sharp melting point. It does mean it undergoes melting and it completely transforms to liquid phase under constant temperature condition, and you can easily see the point A to B, although the time is increasing, that is we are continuously heating the system, but the temperature of the system has remained the same. And then once at point B all of the substance has transformed from solid phase to liquid phase, now we have only the liquid phase in the system, and then the temperature, and if we continue to heat the system, the temperature of the liquid phase continuously lies along curve BC. So, now we need to understand what is basically this heating curve means basically for us, what clue we can draw from this. When we heat the system, here we can see if only a single phase, that is either solid or either the liquid phase exists, then its temperature gets raised. How the temperature gets raised, this question comes into consideration. This can be answered with the fact that when we heat the system, then in that situation we are supplying the heat given to the system is taken up, it is used to raise the internal energy of the system. The internal energy of the system has various contributions, as we had said in the first lecture itself, that it has kinetic energy contribution, the potential energy contribution, and so on. And it is the kinetic energy contribution which manifests itself in the form of temperature rise. And therefore, it means for a solid substance, if we continue to heat the system, the temperature of the system rises because of increase in kinetic energy. Kinetic energy means the molecular motion increases, the extent of molecular motion increases. What it does mean? However, we all know that in solid phase each atom or molecule occupies a fixed position in the crystal lattice of the material, and therefore, it means for a solid phase the molecules or the constituent chemical species does not move. Then how the temperature rises, it is again a question. Basically, we can have a molecular picture as to what happens when we heat the system. When we heat the system, the heat is taken up by the heat is a form of energy, and that energy is taken up by that solid substance in order to excite the vibrational motion of the molecules. Although the molecules are placed at a fixed position, within the molecule there are various bonds which undergo vibrational motion, which participate in vibrational motion, and the participation of vibrational motion actually bring about an increase in temperature. That is how when we heat a solid substance we reach ultimately to point A. Now question arises, what occurs at point A, and so that the temperature of the system continues to remain constant till point B is achieved. Basically what happens is point A represents the melting point of a substance, and therefore if you continue to heat the system, what will happen is at the melting point basically the substance will start liquefaction, that is solid to liquid transformation will go to take place. And therefore it is important to understand that basically it is now not the, therefore whatever heat is given to the system, it is not used to raise the temperature of the system. Basically it is used to raise the phase transformation of the system. So what it does mean, the heat is being taken up by the system, but is not used up to raise the internal energy by virtue of molecular motion, but that heat is used up to bring about phase transformation, that is from solid phase to liquid phase. So it does mean is the same substance in two different phases do have different enthalpies. This is basically a curve between the enthalpy and the temperature of a substance. If a substance is present at a particular enthalpy value at a fixed temperature, it will have a fixed enthalpy value. The enthalpy of the substance will continuously change as it is on this linear curve, and will ultimately reach melting point. As we had seen that in the heating curve, that at melting point the temperature of the system remain constant. The only answer to this observation can be that at the melting point, whatever heat we are giving to the system, that is not used to let the temperature of the system to rise, but that is used to bring about phase transformation from solid phase to liquid phase. So it is very clear that the two different phases of a same substance has different enthalpies at same temperature. So it is that heat which we are continuously supplying is used to raise the enthalpy of the substance from when it undergo conversion from one phase to that of the other. That is the change in enthalpy represent the enthalpy of a physical process called phase transformation. If the transformation of phase is from solid phase to liquid phase, this enthalpy is known as enthalpy of fusion. So basically thermochemistry helps us to determine these enthalpy values of physical transformations, and in addition they also help us to determine the enthalpy of a reaction. But if we want to determine the enthalpy of a reaction, as we have already said, enthalpy of a reaction is if we want to make it only a temperature dependent quantity, then we need to carry out the reaction under standard conditions. That is, for standard condition reaction, we need to specify the standard state of a substance. So let us now first of all define the standard state of a substance. The standard state is the state of a material at a defined set of conditions, and these defined set of conditions is not just but 1 bar pressure, that is the standard pressure. That is what we mean by standard state of a substance is the presence of the substance under standard pressure condition. So if suppose a pure gas we have, then we can define the standard state of a pure gas as the pure gases state of a substance present at 1 bar pressure and at specified temperature. For a pure crystalline substance, the standard state can be defined as the presence of most stable crystalline state of the substance at specified temperature and at 1 bar pressure. Similarly, we can also define the standard state for a liquid. The standard state of a liquid can be described as the liquid which is liquid form of the substance which is present at 1 bar pressure, again at specified temperature. So moreover, we have, if suppose we have a solution, that solution is having ions or a neutral substance, then that substance which is present in solution or ions which are present in solution, their standard state we can also define. A substance or an ion in the standard state at a given temperature is the unit molality of the species, of that ionic species or the molecular species in ideal solution at 1 bar pressure. So it means if we have a solution, then the solute which has been dissolved, for example an ionic substance which furnish ions in solution, or a molecular species which go to dissolve and form a solution, then those ions or molecular species should have their molality, that is 1 unit. The concentration of the solution should be unit molality and solution should be present at 1 bar pressure. Then that substance, that molecular substance or ions will be said to be present in their standard state. So therefore, standard states we have defined in this manner. If a substance is present in standard state, then the molar enthalpy of the substance, that is enthalpy of 1 mole of the substance, therefore under its standard state will be known as standard molar enthalpy of the substance, and is represented by symbol HM standard, again in parenthesis the name of substance, which is followed by the physical state of substance and then the temperature. It is important to note here, now here there is no pressure. Why there is no pressure being specified? Because we have given a superscript degree over the symbol of the molar enthalpy of the substance. That is a degree as superscript which has been applied over in the symbolic form molar enthalpy of the substance. So it means standard molar enthalpy, and standard molar enthalpy is the molar enthalpy of the substance under 1 bar condition. So therefore pressure is fixed, so therefore we need not mention the pressure over here. So therefore standard molar enthalpies of a substance are only functions of temperature. Therefore standard molar enthalpies are temperature dependent quantities only. Having said this, now it is important to define the enthalpy of a reaction. What is basically the enthalpy of a reaction? If you remember, in the up to class 12th standard textbooks, you would have seen this formula that specifies the delta RH, that is the symbol for reaction enthalpy or the enthalpy change of a reaction, that can be estimated as the difference between the sum of enthalpies of the products and the sum of enthalpies of the reactants. What it does means is that if we multiply the stoichiometric coefficient of a particular product along with its molar enthalpy, then we take the sum of this product over all products, then from this total sum if we subtract the sum of products of coefficients, stoichiometric coefficient times the molar enthalpies of the reactants, then it is equal to the reaction enthalpy. So it is very simple, that is the sum of molar enthalpy of products minus the sum of molar enthalpies of the reactants, that is equal to the reaction enthalpy. That is how much there is an enthalpy change when during a reaction reactants do transform from the reactants to the products. So products are the products represent the final state of the system and reactants do represent the initial state of the system. So final state minus the initial state becomes equal to the reaction enthalpy. So basically the enthalpy change of a reaction or the reaction enthalpy is just nothing but the sum of molar enthalpies of the products times the stoichiometric coefficient minus the sum of molar enthalpies of the reactants, each being times with a stoichiometric coefficient. So now if we want to see how this formula has come up, then it is important to formulate certain important concept, and that concept is the extent of reaction. So let us have a look at what is the extent of reaction, which we need to formulate here. It is now should be taken into consideration that the progress of a reaction is stated by defining the physical quantity known as extent of reaction. What we mean by saying this is that suppose a reaction progresses. When a reaction progresses, the reactants are consumed and the products are produced, and the amount of a reactant consumed, if we divide it with the stoichiometric coefficient of that particular reactant which appears in a balanced chemical equation, then it represents the extent of reaction. Extent of reaction basically gives an idea about to what extent the reaction has proceeded in the forward direction. The amount of a reactant consumed or the product formed in a balanced chemical equation is equal to the stoichiometric coefficient times the extent of reaction. So, it means if we want to determine after any point of time what is the amount of reactant consumed or amount of product formed, then all we need to do is if we have the quantity extent of reaction, then multiply it with the stoichiometric coefficient of that particular reactant or product. That is it. That will give us the amount of reactant consumed. Let us have a look at at this point by considering a particular reaction, that is we are considering the decomposition of dinitrogen pentoxide which is present in the gaseous phase, its decomposition. When it do decompose, it do form nitrogen dioxide and also forms oxygen. So, for every 2 mole of N2O5 being consumed or decomposed, 4 mole of nitrogen oxide nitrogen dioxide is produced, along with 1 mole of oxygen is produced. So, suppose that we had started in the reaction mixture with N0. This N0 represent the initial number of moles of N2O5, the reactant being present initially in the system. Now, as it was said in the previous while showing the previous slide, that after time t, if xi, this xi represents the extent of reaction, that is it gives us an idea about to what extent the reaction has proceeded in the forward direction, and it has unit of the amount of substance, that is mole. And if we multiply xi for that reaction at time t with the stoichiometric coefficient, then it represents the amount of that species either consumed, that is used for the reactant, or is produced, that is used for the product. So, if we want to estimate the amount of dinitrogen pentoxide after a time t, when some amount of dinitrogen pentoxide is decomposed, then all we need to do is we need to make it equal to the initial amount of dinitrogen pentoxide minus the amount of N2O5 which has been consumed during decomposition, and that is equal to 2, which is the stoichiometric coefficient of dinitrogen pentoxide in this balanced chemical equation, multiplied with the xi, the extent of reaction, which has the unit of number of moles or amount. So, therefore, N0 minus 2 xi is the amount of dinitrogen pentoxide after certain time t, when the extent of reaction is xi. So, initially there was no nitrogen dioxide present in the system. So, we have taken its initial amount as 0, plus now we can add to this after time t whatever due to the decomposition of dinitrogen pentoxide, since nitrogen dioxide gets formed. So, therefore, we need to, if you want to determine that how much amount of nitrogen dioxide is formed, then all we need to do is we need to multiply the stoichiometric coefficient of nitrogen dioxide which is acting as a product in this balanced chemical equation, and multiply it with again xi, the extent of reaction, that gives 4 xi as the amount of nitrogen dioxide produced. And so, similarly we can say amount of oxygen produced is only xi, as 0 was the initial amount of oxygen we had not taken in our system. So, therefore, N0 minus 2 xi is the amount of dinitrogen pentoxide after certain time t, and this 4 xi is the amount of nitrogen dioxide after time t, and xi is the amount of oxygen after certain time t again. So, now the enthalpy of a system at a stage when reaction has proceeded in the forward direction after time t, then we can estimate the enthalpies, that is the final enthalpies. That is how we can determine the final enthalpy of the system. That is, we need to multiply the number of moles of each chemical species which is present after time t with its molar enthalpy. That is, N0 minus 2 xi is the amount of dinitrogen pentoxide which was present after time t in the system. We need to multiply its number of mole, that is N0 minus 2 xi, with the Hm, the molar enthalpy of dinitrogen pentoxide, plus we need to add to this is the number of moles of nitrogen dioxide, which needs to be multiplied with the number with the molar enthalpy. So it is the enthalpy contribution of nitrogen dioxide which was remaining after time t, which was present after time t, and there was xi mole of oxygen were present after time t. So therefore molar enthalpy of oxygen at specified temperature, when you multiply it with xi, it gives the enthalpy contribution due to oxygen itself. So there were 3 chemical species which were present in the system, and we add the enthalpy contribution of each chemical species after time t, then it becomes the final enthalpy, that is the enthalpy after time t of the system. Similarly, we can say initial enthalpy of the system is given by N0, that is initial number of moles of N2O5. This N0, initial number of moles of N2O5, when we multiply it with molar enthalpy of N2O5, this is N0 HM N2O5. So this is the initial enthalpy of the system, because at initial state, when reaction had not proceeded in the forward direction, no product species was present, only reactant species was present. So therefore contribution towards enthalpy can only be considered due to only the reactant species. So this is the final enthalpy expression and this is the initial enthalpy expression. If we take the difference of final enthalpy, final enthalpy minus initial enthalpy, this represents delta H, that is the enthalpy change of the system, which is just nothing but N0 minus 2 xi Hm. That is, in the previously we have seen, this is the final enthalpy minus this is the initial enthalpy. And if we open these equations, and then we get to see that N0 Hm and N2O5, these are common, and so therefore with opposite sign these do cancel, and therefore equal to this, with this expression we have delta H of the system, that is an enthalpy change of the system. Mind you, we are only considering the enthalpy change of the system, we are not talking about reaction as yet. So that is equal to minus 2 xi Hm N2O5 plus 4 xi Hm NO2 plus xi Hm O2. So therefore before we go any further, let us have a look at the unit of enthalpy change, that is unit of delta H is equal to, here you see in each term we have the xi value, the xi function and the molar enthalpy function. So each term has its unit in a way that it has unit of xi multiplied with unit of Hm molar enthalpy. So unit of xi, as I had specified earlier, is mole, the amount of substance, and that needs to be multiplied with unit of molar enthalpy, that is kilojoule per mole. So therefore per mole do cancel with mole, and therefore we end up with having unit of delta H as kilojoule only. That is the unit of enthalpy change of the system. Till the point of time I have not correlated this example with the reaction enthalpy. So now it is time to define the enthalpy of reaction. The enthalpy of reaction is the enthalpy change for the unit extent of reaction. So therefore in this equation, in the right hand side, if we take xi common from all these right hand side terms, and then we take this xi to the denominator of left hand side, we would get is delta H by xi. So that is equal to delta RH, or in other words the reaction enthalpy. The enthalpy therefore, and the enthalpy of a reaction is the enthalpy change for the unit extent of reaction. That is, the enthalpy of a reaction is the enthalpy change of the system with unit extent of reaction. So it is represented by symbol delta RH. So therefore delta RH is equal to delta H by xi. Now let us have this delta RH. Now let me specify that this delta RH is just nothing but the symbolic representation for reaction enthalpy, or the enthalpy of reaction, and that is equal to delta H, the enthalpy change of the system, divided by the extent of reaction xi. So the unit of delta RH is equal to unit of delta H divided by the unit of xi, and the unit of delta H is kilojoule and the unit of xi is mole, and therefore it should be made very clear that the unit of delta RH is kilojoule per mole. Having said this, now it is further needs to be given an important consideration how to determine the enthalpy changes. So, since the enthalpy of reaction is defined as the enthalpy change for unit extent of reaction, the amounts of reactants consumed and the products formed will be equal to the corresponding stoichiometric coefficients expressed in mole. It means that if you want to keep xi, the extent of reaction, as 1, it means you need to specify first of all the balanced chemical equation. Over here, for example, we have given one balanced chemical equation as 2N2O5 gas to 4NO2 plus O2. It means xi is 1 in this balanced chemical, for this chemical system, when 2 moles of dinitrogen pentoxide is decomposed to form 4 moles of nitrogen dioxide along with 1 mole of oxygen is also formed. Then in that situation we would call the xi for this balanced chemical equation reaction equation system, the xi is 1, and the delta H of such a system would then be the delta RH, the reaction enthalpy of this particular reaction. The enthalpy of reaction therefore refers to entire chemical equation and not to any particular reactant and product. We are not saying that when so and so mole of nitrogen dioxide is formed, then it is the reaction. Sometimes we make a misconception by saying that 1 mole of so and so product is formed in a reaction, then we call it the reaction enthalpy. But it should be made very clear that reaction enthalpy means the enthalpy change of the system for unit extent of reaction, that is reaction has proceeded in forward direction according to the xi value, that is unity. For xi value to be unity, it should mean that if we consider a balanced chemical equation, the number of moles of the reactants corresponding to the stoichiometric coefficients, they have been consumed, and the number of moles of the products corresponding to the respective stoichiometric coefficients of the respective products have been produced in the reaction system. Now, again consider the fact that since enthalpy of a substance can change with temperature and pressure, so it is therefore important that the reactants and products should be specified at definite temperature if we want to consider the enthalpy change. So, while we carry out enthalpy change, as we have seen earlier, the formula for calculation of reaction enthalpy is the stoichiometric coefficient times the molar enthalpy of products, we should take its sum, and from this we should subtract the sum of various terms which represent the stoichiometric coefficient times the molar enthalpy of reactants, and these stoichiometric coefficients would then serve as the number of moles for unit extent of reaction. So, it is important to note that these molar enthalpy values of a particular substance which we are taking, they should be at a same temperature. Why they should be at same temperature? Because each substance, as we had seen earlier, the enthalpy of a substance varies with temperature as well as pressure. So, pressure we can keep it fixed, but when we make the temperature of the system rise, then again the enthalpy do changes. So, therefore, for the purpose of calculation of enthalpy change of a reaction, enthalpy change of a reaction is calculated under constant temperature condition. Now, since enthalpy of a substance, as I said, is a function of temperature as well as of pressure, and I had already specified that the pressure dependence of enthalpy can be reduced by considering the molar enthalpies of the substances at 1 bar pressure. Under those situations, molar enthalpy will be the standard molar enthalpy, and the standard enthalpy change will then be the applicable term there. Rather than just the enthalpy change of the reaction, we would then deal, if a reaction is carried out under standard conditions, the standard enthalpy change of the reaction, that will be applicable rather than just the enthalpy change. So, standard enthalpy change of a reaction means the enthalpy change when all the reactants and products are in their standard states. Now, having defined this enthalpy change of a reaction, let me emphasize further that it is important to have the molar enthalpy values. But is it possible to have absolute molar enthalpy values of reactants and products? That is a question which we need to answer. Before we go further on to this discussion, how to determine the molar enthalpies of various reactants and products, let us have a look at the sign convention or the sign of molar of enthalpy of reaction. Just have a look at this. There are two kind of reactions, we all know, depending upon whether the heat evolves or is used up in carrying out a reaction. So, on the basis of which we define the reactions as endothermic reaction or exothermic reaction. So, let us have a look at what we mean by endothermic reactions. This we would like to consider in simple textbooks from the thermodynamic consideration. It is important that thermodynamics, since deals with only macroscopic systems, so therefore molecular picture it does not take into account. But we can understand the endothermic nature of a reaction from the molecular point of view. So, let us have a discussion of the endothermic nature of a reaction. To consider this, let us see what happens in a reaction. When a reaction occurs, during the course of a reaction, what happens? Some bonds are broken, the bonds which are present in the reactants, and some bonds, new bonds are made, new bonds are formed. Those bonds are formed which lead to formation of product species. The products of the reaction have, when the products of the reaction have more chemical potential energy than the reactants. Now, you please have a look at this diagram. We can easily see it is a diagram between the potential energy of the system and the reaction pathway. Reaction pathway means the coordinates of the reaction system. So, here we have reactants. Reactants have less potential energy, and when they undergo transformation from reactant species to product species, the products do have greater potential energy. So, what there is a increase in potential energy corresponding to this C region. We can easily see that the potential energy of the reactant is lesser and the potential energy of the product species is higher. So, therefore, it means when a reactant in a reaction do transform to product, in these kind of reactions, the potential energy of the reaction system do increase. So, to acquire this extra energy, from where this energy will come? Some of the thermal energy of the surroundings is converted into chemical potential energy, that is stored in the form of potential energy of the products. So, therefore, that energy if comes from the system, then if that energy comes from the system, then it will lead to a relaxation in the molecular motion of the various chemical species which are present in the system, and which manifests in the form of temperature, and as a result, if those extent of molecular motions do decreases, the temperature will decrease. So, it means the energy of the system when in a reaction the reactants do transform to the products which have higher potential energy, the kinetic energy of the constituent chemical species within the reaction system has been utilized to store them in the form of the potential energy of the products. As a result, whenever an endothermic reaction occurs in an adiabatic environment, then the temperature of the system would fall. Otherwise, what will happen is that in order to maintain the temperature, some heat from the surrounding will enter the system and will be used to raise the or will be used to restore the temperature of the system if the reaction is carried out under constant temperature condition. So, this is how we define the endothermic reactions. Endothermic reactions therefore occur with an absorption of heat, and consequently the delta H is a positive value. The enthalpy change of endothermic reaction is a positive value because molar enthalpy of products is greater than that of molar enthalpy of reactants. And what is enthalpy change of a reaction? Sum of molar enthalpy of products each times the stoichiometric coefficient, from which you need to deduct the molar enthalpy of reactants, that becomes the molar enthalpy of the reaction. Now, coming over to exothermic reaction, the situation in an exothermic reaction is completely reversed. Basically, here the reactants have greater chemical potential energy. Chemical potential energy means if suppose there are some bonds which have some bonds are placed which has less, which are weaker bond. So, in that situation, by virtue of absorption of energy, the bonds are weakened. So, in that sense, the potential energy is increased of the system, but there is greater forces of interaction which operate between the atoms to bring about a bond, then the bonds are stronger and potential energy of the system gets decreased. So, it means in an exothermic reaction what happens actually is that during the course of a reaction again some bonds are broken and some new bonds are formed. The products of the reaction have less chemical potential energy than that of the reactant. So, obviously, if the potential energy of the reactants is greater than that of the potential energy of the products, then the potential energy which is stored in the reactants would then appear as heat in order to allow the transformation of reactants to those of products, and that heat will be released in the system. So, that will, if the reaction is carried out in an adiabatic condition, so therefore, the temperature of the system will rise. Otherwise, the heat that would release because of the progression of the reaction in forward direction, that would be transferred to the surrounding. So, now in this manner we can define exothermic reactions as those reactions which occur with a release of heat. Having said this, now let us have a look at the relationship involving reaction enthalpies. When a reaction, if suppose as I said that we need to write a balanced chemical equation, and for which the enthalpy change of the reaction system for unit extent of reaction is its reaction enthalpy. So, we can consider this first equation. Here carbon in solid form combines with oxygen gas and forms carbon dioxide. So, 1 mole of carbon combines with 1 mole of oxygen and 1 mole of carbon dioxide is produced, and the change in enthalpy of the system for this unit extent of reaction is minus 393.5 kilojoule. That is, this much heat is evolved. So, if we double the quantity of the substances which are involved in the chemical reaction in the reaction system, then the enthalpy change in the system would obviously get doubled because the substances are doubled. So, therefore, when a reaction is multiplied, this is what we mean to say by this is that if we multiply a reaction by a factor, then the enthalpy change of this reaction system is also multiplied by the same factor. What we mean to say by this is that if suppose for 1 mole of combination of carbon and oxygen, when 1 mole of carbon dioxide is produced and delta H is minus 393.5 kilojoule, if we multiply this reaction by 2 as 2 moles of carbon plus 2 mole of oxygen to 2 mole of carbon dioxide, then we also need to multiply the enthalpy for this reaction system with 2, and will ultimately be equal to 787.0 kilojoule. Another point is that if a reaction is reversed, that is, if suppose now we write this reaction in a reverse manner, that is when carbon dioxide to decompose and form carbon solid in the solid phase plus oxygen gas, then the sign of this initial reaction needs to be reversed, because we have reversed the direction of the reaction in this second reaction. So, therefore, it means now you can see here, when carbon combines with oxygen forms carbon dioxide, since its delta H is minus 393.5 kilojoule, then if we reverse the direction of the reaction, then the delta H, the enthalpy change of the reaction, the sign of enthalpy change of the reaction would also be reversed, but the quantity of delta H, that is the enthalpy change of the reaction in magnitude, will be the same, but its sign will gets reversed. It means if combination of carbon and oxygen to form carbon dioxide is an exothermic process, then the decomposition of carbon dioxide to form carbon in solid phase and to release oxygen, that is the reversal of the earlier specified reaction, would be a endothermic reaction rather than an exothermic reaction. So, having said this, now we need to focus our attention to another point, that how to determine these enthalpy change for a reaction. So, since we had till the point of time seen that enthalpy change of a reaction is sum of molar enthalpy of products minus the molar enthalpy of sum of molar enthalpy of reactants. It means molar enthalpy of the product chemical species and the values of molar enthalpies of reactant chemical species are important values if we want to determine the molar enthalpy of a reaction. So, but determination of absolute molar enthalpy values of various chemical species is an impossible task in that sense, because we cannot determine absolute values of molar enthalpies of substances. Then we need to define another concept if we want to determine the enthalpy of reaction. What is that concept? That concept is molar enthalpy of formation. So, let us have a look at what is molar enthalpy of formation. You see, the standard enthalpy of formation, that is, if all the reactants and product species are specified under standard conditions. The standard enthalpy of formation, that is given the symbol delta HF standard, is the enthalpy change accompanying the formation of 1 mole of a pure compound from its constituent elements in their standard states. What it does mean? If suppose carbon is an element in its most stable state of aggregation in standard state, and oxygen, that carbon is in the form of graphite. Graphite is the most stable state of aggregation of carbon in solid phase under standard condition at 298 Kelvin. So, therefore, under standard condition means 1 bar pressure. So, therefore, if we want to determine the enthalpy of formation of carbon monoxide gas, then let us have a look. Just we have defined that the standard enthalpy of formation is the, first of all, it needs to be emphasized that standard enthalpy of formation is only for a compound and not for, and we are not considering here for any other species, the compound which is made up of elements. So, therefore, molar enthalpy of formation is the enthalpy change accompanying the formation of 1 mole of a substance under standard conditions from the constituent elements in their most stable state of aggregation, again under standard condition at specified temperature. That is how we define the standard molar enthalpy of formation of a compound. So, it means the compound which should form should be 1 mole. The quantity of compound is being specified in the enthalpy of enthalpy of formation. Let us have a look at it with the help of an example. How we can write formation reactions. Suppose we consider the formation reaction for carbon monoxide gas from its elemental elements, that is carbon and oxygen. The formation reaction is the reaction between the elements in the compounds, that is, which are carbon and oxygen here. So the elements must be in their standard state 1. Standard state means, and that too the most stable state of aggregation. There are several forms of solid carbon, but the one with enthalpy of formation, that is of elements is 0, is graphite. That is, its most stable state of aggregation of carbon is graphite under standard condition. And oxygen is present in the gaseous phase. So oxygen standard state is the diatomic gas. It is not a monoatomic gas under standard condition. So therefore oxygen is diatomic in nature in gaseous species under standard condition. So carbon solid in the form of graphite, which when combined with oxygen gas, these are two stable state of aggregation of the elements carbon and oxygen. They go to give carbon monoxide gas. The equation must be balanced. Now we can see there is an imbalance in the equation. Why there is an imbalance in the equation? Because in carbon monoxide we have only one oxygen atom, whereas in diatomic oxygen species there are two oxygen atoms are involved. So we need to balance this equation, but we need to balance it in a way that we need to be sure that the compound that which we are interested in, that is carbon or monoxide, should have only unit stoichiometry, because we want only 1 mole of carbon monoxide to be formed by combination of carbon and oxygen. So therefore in order to balance this equation, we need to multiply as the stoichiometric coefficient, that is half unit, to the oxygen in gaseous species. So that is how we achieve a balanced chemical equation, and for this we can determine the enthalpy of formation as the enthalpy of formation of compound carbon monoxide. We would continue the discussion of enthalpy of formation and how we can utilize the enthalpy of formation data for calculation of enthalpy change of a reaction along with the enthalpy of combustion and several other enthalpies in subsequent lecture. So for the time now, we take a goodbye. Thank you so much.
With this note, thank you, sir. Thank you so very much for giving us a productive session. Dear friends, if you want to give your feedback regarding this particular lecture, then you can mail us at info.cc@nic.in. In fact, you can ask your questions through mail, and we would love to solve your question the next time when Dr. Amit visits our studio. Till then, take care. Goodbye. Thank you, sir. Thank you so very much.